All right, welcome everybody to the first club meeting of the summer. Yeah, we'll go ahead and get right into it. First thing on the agenda, or on the agenda for this meeting is of course trivia. So if yeah, we don't have any Zoom participants as of yet, but please, you both feel free to participate in trivia. I've created some very very good questions this week. Only three questions this time instead of five. But yeah, just turn your answers in for every question that we ask, and you'll get varying amounts of points for each question you get right. And then there will be a bonus question where you can wager your points that you've earned in the previous questions. All right, so first question. On this day in 1952, which computer company announced its first electronic computer, the Model 701? Worth 1 point. All right, go ahead and get your answers in. Nice. So the correct answer for that question is IBM's. Yeah, at the time, IBM was the world's largest supplier of punch card equipment and supplies, so building a computer was seen as a radical departure within IBM. A major reason IBM built the 701 was that it was described to be IBM's patriotic chairman, that it was described to IBM's patriotic chairman, Thomas Watson Sr., as a defense calculator that would assist the U.S. in fighting the Korean War, which had just started. 19 of the machines were sold mainly to the government, military installations, and West Coast aircraft manufacturers. They rented it for $8,000 per month, equivalent to $56,000 per month in 2010. Yeah, pricey machine. All right. Question two. GIT is an acronym that stands for what? I actually just learned this one like 2 weeks ago, I think. All right, about 10 seconds left for this one. All right, go ahead and get your answers in. GIT is an acronym that stands for what? Global Information Act. Yeah, makes a lot more sense to me. All right. Question three, worth 4 points. When solving systems of linear equations, which iterative method can only be used with Hermitian matrices? We got conjugate gradient, GM-res, Arnoldi iterations, and biconjugate gradient. This is called back to Math 571 or scientific computing, talked about in both those classes. All right, about 10 seconds left on this one. All right. So, which of these, when solving linear systems, which iterative method can only be used with Hermitian matrices? Conjugate gradient method. It turns out that the Arnoldi iteration is not even for solving systems of equations, but it's actually used to find eigenvalues. GMRes and biconjugate gradients can be used with non-Hermitian matrices as well. Oops. So that is the end of our typical round. And then the bonus question has to do with Python data types. So go ahead and write down your wager if you want to. In first place, we have Brandon with 5 points, and in second place, we have Tim with 1 point. If you don't want to wager, you do not have to turn, or if you want to wager everything, you don't have to turn a card. But if you want to wager something specific or 0 points, go ahead and send in your bets. All right. The question is, name 3 native data structures available in Python, and also in naming them, describe how to initialize them using like the keyboard symbols, not like any special like function or anything. Okay, about 10 more seconds left on those answers. All right. The 4 native data structures available in Python are the set, the dictionary, the list, and the tuple. The set and the dictionary are very similar in how you initialize them, but what you put inside of them will determine if it's a set or dictionary. So, oof, very close on the bonus question for both parties. In first place, we have Brandon with 2 points, and in second place, we have Tim with 1 point. All right, that um, that concludes our trivia session, and now we'll get on to our presentation for this week. This week, I'll be presenting a presentation I'm presenting in a conference coming up soon, and it has to do with my research, reconfigurable partition systems, and being used in adaptive modular construction. The beginning half of this is not so scientific computing related, but the end is where I really have to, really the research wouldn't be possible without the use of computers. So yeah, with that, this presentation is all about a design of a reconfigurable partition system that will help make modular construction more adaptive. So modular construction is the practice of prefabricating many instances of volumetric or planar units of varying degrees of finish in an offsite or controlled environment, then transporting those units to the construction site for rapid and easy assembly. So here you can see an example of what a relatively unfinished volumetric unit might look like. Modular construction has seen increased usage recently because of its ability to decrease construction timelines and cut costs. One study identified that construction schedules could potentially be cut in half, and a cost savings of up to 50% might be realized if modular construction is used instead of traditional construction. Some notable examples of modular construction are the J57 tower, which is a 57-story tower that was assembled in only 19 days, and the Atira student accommodation that has reduced its construction timeline by 30% compared to a traditional construction method. The efficiencies of modular construction are driven by the repetitive use of identical modules, the the high quality production environment of offsite facilities, and the ease of on-site assembly, requiring a smaller on-site workforce. However, these factors comes with drawbacks, them being one, that modular construction, as it is now, needs a high degree of architectural repetition, making it unsuitable for buildings that have any sort of variety. And two, even though the modular units are fabricated separately, once they are assembled, they often lack the ability to be reconfigured or reused in other projects. So this lack in versatility makes modular construction unsuitable for many construction projects. So there has been a growing interest to make modular construction more versatile while keeping the benefits of offsite construction and the easy on-site assembly. So with these goals in mind, we decided to investigate adaptable modular partition systems, and we developed what we call an internal accordion wall, which expands and contracts by way of these accordions on its inside. The system is versatile because many instances of this partition system could be assembled end to end, varying their expansions and contractions to accommodate more varied architectural designs. This partition system would also retain the efficiency of offsite fabrication because only a few different unit designs would be used, and you're still achieving this wide variety of architectural variety. Other advantages of the system include its ability to accept different infill materials since it's a hollow partition, enhancing the acoustic, thermal, or structural properties. And it can also be reconfigured post-installation, allowing its use or its purpose to change as the use of the building changes, or even allowing it to be reinstalled in other buildings. However, in this presentation, we mostly want to focus on the geometric and kinematic properties of the system and why this design specifically for a partition wall has unique advantages over other adaptable and versatile partition walls. And so, yeah, inside of the geometric and kinematic analyses, there's that's where most of the computational science is, for this system. So starting with the geometric properties, since the wall has the same depth in the expanded and collapsed configurations, the percentage increase in volume can be calculated by simply calculating the percentage increase in length. The percentage increase in length, signified by eta exp expansion, and the depth of the wall, d, can both be determined in terms of the lengths of the interior accordions. For a specified depth, a variety of expansion ratios, that's the eta exp, can be determined. So you can see here at the 15 unit depth that you can traverse across a number of these contours for the expansion ratio. If only one expansion ratio is used in a series of wall units, then the number of units plus one configurations are possible. However, if two expansion ratios are used, n1 plus one times n2 plus two configurations are possible. Then if n expansion ratios are used, then it becomes an exponential relationship between the number of expansion ratios you have in your series of wall units. Yeah, and the amount of configurations that you can have. Moving on to the kinematic discussion, we'll start by looking at one kinematic path of this internal accordion wall. So starting with the compact configuration, in order to expand the internal accordions, you first have to go through a panel dilation. Once the panel is dilated, the internal accordions can be extended, and then the dilation can be reversed in order for it to recuperate its original depth. So this is only one kinematic path possible for the system, and it's highly mobile otherwise. For it to be used as a structure, it must become rigid in its expanded and collapsed configuration. Traditionally, a deployable structure is made rigid by locking the rotational hinges or other degrees of freedom. To determine which degrees of freedom need to be fixed for rigidity, we analyze both configurations under a variety of external constraints, such as locking the rotational hinges. Our rigidity analysis started by idealizing the system as linkage systems, and here you can see the linkages in both the expanded and collapsed configurations. Then admissible configurations of the system were defined by parameterizing the positions of linkage nodes and constraining those parameters. If all the node positions are contained within a single vector, then the position of a single node can be achieved with a mapping matrix. Using the positions of a single node, we then defined several constraints for our linkage system. First, we defined a linkage rigidity constraint by constraining the norm of the vector, that is the difference between the jth position and ith position. So A is pj minus pi, and then constraining the norm of that with the original length. So this would define one constraint equation. And then we also defined a fixed angle constraint by creating a vector A between nodes I and J and a vector B between nodes I and K. And then fixing these two vectors, the angle between these two vectors using a dot product. Finally, some linkages in our idealized model connect to the midspan of other linkages. This type of connection can be realized through our constraints by using the previous two constraints. If vector A is defined between nodes I and K, and vector J is defined between nodes I and J, then using the previous two constraints, this new constraint can be realized. With these constraints defined, we found the infinitesimal rigidity of the configuration shown on the right by analyzing the null space of the rigidity matrix. According to rigidity theory, a rigidity matrix can be formed from the gradient of each constraint imposed on the parameterized motion of the system. If the null space of the rigidity matrix is empty, the structure is infinitesimally rigid. However, if any vector exists in the space, then those correspond to admissible infinitesimal velocities. So this is similar to solving a system of equations, but the equations are defined by the linearization of the constraints in the previous slide. So that's the rigidity for the expanded configuration. However, for the rigidity of the collapsed configuration, we incorporated contact constraints and needed to use an alternative method for rigidity analysis. This is necessary because contact constraints are naturally represented as inequalities and are not compatible with the systems of equations needed for the null space analysis. An alternative method we used was the configuration space approach. So a configuration space is an n-dimensional space for a linkage system with n degrees of freedom, where admissible configurations are delineated from non-admissible ones. The bottom left shows a simple linkage system and its circular configuration space. Similar to this, an infinitesimal configuration space is a linearization of the original configuration space. And it delineates admissible velocities from non-admissible ones. So according to rigidity theory, a rigid configuration space corresponds to an isolated, or a rigid configuration corresponds to an isolated point on this configuration space. So this linkage we have shown here would not be rigid. And an infinitesimally rigid configuration would correspond to an empty infinitesimal configuration space. Again, looking at this infinitesimal configuration space, if there were no line there, it would be rigid. We chose to construct the to analyze rigidity, we chose to construct the infinitesimal configuration space using the cylindrical algebraic decomposition algorithm, which in essence takes a set of polynomials. It takes a set of parameterized constraints in polynomial form and returns explicit definitions for each degree of freedom, each degree of freedom's admissible regions in a tree-like structure. So to consider contact, we also needed to define additional contact constraints. And these constraints we added were both node linkage and node-to-node contact conditions. However, contact detection was implemented to reduce the number of constraints added for contact. Only pairs that were within a predefined distance of each other were constrained by contact. For every node and linkage pair, the contact detection first considered a node to linkage contact condition. Then if that condition wasn't present, it would consider a contact with the nodes of the linkage. Similar to our previously defined constraints, vectors A and B can be defined from nodal positions. The node to linkage constraints were then based on vectors D and gamma, which are decompositions of vector B onto an orthogonal basis constructed from vector A. The resulting constraint is that the vector D does not decrease in magnitude, and this constraint only applies if D is less than some pre-specified distance D naught and is within the length of the linkage, which is determined using gamma. I guess I should say gamma and A. So if these conditions are not met, then it's still possible that the node-to-node contact condition could still arise. This constraint requires that the magnitude of vector B does not decrease and is only activated if the magnitude of B is less than D naught, as you can see here. So once the linearized constraints were determined, for the collapse configuration, they were used as input to the cylindrical algebraic decomposition algorithm. For the infinitesimal configuration space, the algorithm returns the admissible infinitesimal velocities for the current configuration in a tree-like output. So 2 types of responses can occur in this tree-like format. A tree containing non-zero admissible infinitesimal regions corresponds to a linkage system that is infinitesimally flexible, like this tree on the left where V0 can be something non-zero, and then the rest of the parameters V1 and V2 can be determined based on the definition of V naught. But a result where the only admissible velocity is the zero velocity, as shown on the right, corresponds to an infinitesimally rigid linkage system. So using the CAD algorithm, we determined that fusing the indicated nodes such that the horizontal and vertical velocities are equal for both of these nodes, that will create a rigid system. So comparing this rigid configuration, where only 2 nodes need to be modified, versus the one for the expanded configuration, it's apparent that considering contact makes for a much more efficient constraining process. This is an important factor in offsite fabrication and also for ease of assembly when considering this wall. So in conclusion, the internal accordion wall has geometric and kinematic properties that make it advantageous for being used as a versatile and adaptable partition wall. Stowing the accordions in the internal chamber of the wall allow it to have a relatively flat surface and constant depth in the expanded and collapsed configurations, as opposed to a traditional accordion wall. The occurrence of contact in the wall's collapsed configuration allows it to become rigid by only adding 2 mechanisms to the wall's exterior. And finally, the expansion ratio can be varied while holding the depth of the wall constant. exponentially increasing the lengths these walls can accommodate with increased variation of expansion ratios. Okay, that is my presentation.
Cool.
Do you guys have any questions?
Yeah, I have one question. I also have a piece of advice about the inequality constraints.
Yeah.
So when I took a class on linear programming, I know there's like a very straightforward technique to turn inequalities into equality constraints.
Mm-hmm.
You just have to introduce another variable. And like if you look up in a web page or something, you'll see that very quickly. I think they call them slack variables.
Okay.
And then so maybe you could then define a linear system that in like actually just states your context straightforward, and then you can do the same null space analysis. And then my question was about something I think that you also concluded on. I didn't, I think it was on slide 4. You talked about like combining walls of different expansion ratios or something like that. I didn't visualize what that would look like.
Yeah. Go back. So this, say this wall is designed with certain lengths for these interior pieces. So this length is about half the length of this one.
Right.
And because of that, it'll expand. Because of that, it has a certain depth and it'll expand a certain distance past this initial configuration.
Okay.
If you change the length, you can change the length of these internal parts so that it expands less, but still keeps the same overall depth here.
Okay.
And so if you like if you just had all the same dimensions here, and you had say like you had 3 of these back to back.
Okay.
There's 4 different configurations or 4 different unique lengths, I guess you could have for the wall at a maximum. But if each one of those was a had a different expansion ratio, they would expand at different lengths, and you'd have more combinations of lengths to choose from.
Cool. And that helps with like addressing the variety
Exactly.
of like the superstructure that you can make.
Yeah.
Cool.
Okay.
Do you guys plan to do any like structural analysis on these at some point?
Yeah, that's probably what I'll work on next
Cool.
after like because yeah, the first step was like looking at the kinematics and then so this panel like actually resembles a like just the unit of it resembles like a sandwich panel a lot, and those have a lot of benefits in terms of like out of plane bending and stuff like that.
Cool.
So just this and at a traditional partition wall, what you usually have is like a stud and then drywall on each side. And so you can kind of see that's also what's happening here. You have this sort of like diagonal stud in the middle.
Gotcha.
And then so I think that we think that the structural properties will be pretty good for yeah, for this partition.
Cool.
Okay, back to our other slides. So just going to give you some updates on our projects. This for the Solid Viz project, there's been some new tasks that are ready to work on, such as developing a set of routines to connect Blender to Python, defining an input file format, and scene preparation. And that's just like getting all the backgrounds and stuff ready for whatever sort of visualization you want. But I also I manually made sort of this video using a simulation that Sam has for like the gravity of these bodies. And so this is, I think in Sam's simulations, this was like a near miss scenario where one body would be orbiting another body and come very close to it all the time. It's other bodies in the picture, but it doesn't really affect it very much. And so, yeah, this is just kind of I just kind of want to make an example of the kind of things that we might be able to do. So all this is tracking rigid bodies, and you can actually program the camera to track certain rigid bodies if you want to, make your animation like that. So just a little bit of update there. And then coffee hour, yeah, of course, still doing the coffee hour. But then also, something I noticed today actually is that the Mujo coffee and the Duderstadt now has mobile ordering. So I think that we'll start doing the North Campus locations too, as well as Central Campuses at the Duderstadt. So it'll probably be every other week that one week we're doing it at Duderstadt, the other week we'll be doing it at the M36 roasters. And I'll skip this. I guess I'll say it for the sake of recording. Well, we're also looking, the outreach committee is looking for some members. So if you're interested in joining the outreach committee, feel free to contact me, Jacob Pavelka. Um, and so some of the things we do in the outreach committee are make advertisements, kind of like the ones you see on the right here. Then creating and distributing these advertisements, sending out meeting reminders, managing social media accounts, which we have none of so far, but maybe in the future, and then the coffee hour. Okay, that's it for our meeting. Thank you guys for being here.